Hi class, so this is part B. It's strictly related to part B, and it may seem like it jumps all over the place, but this is a lot that is related to what's being asked. And for some of you, I teach many classes and every class is doing a portion of this lab, but not every chemistry is at the same level. So I may explain too much, and for some it may not be enough. Okay, so let's get started. Hopefully though, for those that it will help understand, and you have your book to go back over it, and you can always ask me if you need help. So Lewis structures, I posted there is a link to how I put Lewis structures together. You should take a look at that. Look at how the book tells you how to do it, lectures, and then implement what works best for you. So Lewis structures, I kind of already covered this page, so I'm going to skip over this right now, and this page as well. Okay, so let's get to here. Electron groups. Electron groups are what is attached or interacting with the center atom. None of this specifically says center atom, but that's how we're looking at it. So here again is a triple bond, but it's still counted as one. And then there is a single bond, it's still counted as one. If there was a lone pair on the carbon, that would still be counted as one. What happens though if you have molecules that have more than one center atom? So I'm going to go over these to show you how you break it down. Let's say we have this one here. We have 3 carbons. So this is a center atom, this is a center atom, and this is a center atom. The 1 and the 3 look alike. They're very symmetrical. But the one in the middle is not. So the first thing that we're going to pay attention to is you're going to draw an imaginary line. So think of it as just the carbon. We don't care about everything attached to the carbon at this point, because the only things that are attached to this first carbon is a carbon and 3 hydrogens. Everything else after is attached to the middle carbon, and we don't worry about that one right now. So when we look for electron groups, we count 1, 2, 3, 4. So this one's going to have 4 electron groups attached to it. Now if we look at the middle one, we don't care about the hydrogens. We only care about the carbon-carbon bond here and the carbon-carbon bond here. So if we look here, we count 1, 2, 3. We have 3 electron groups attached. We do not care if this is a single bond or a double bond. It does not matter. We count it all as one attachment. And then the same here will match this one. So this one will have 4 electron groups. This one is symmetrical. Symmetrical meaning that it's a mirror image of each other is the best way kind of to explain that. And so these should end up with the same amount of electron groups, and it does. So this is 1, 2, 3 for first carbon, and 1, 2, 3 for the second carbon. Hopefully that helps you understand. You have to break it down. Some of these molecules may have more than one center atom, and you have to strictly look at what's it's attached to, and you do not care whatever anything's attached to that other atom. All right, so again, I've covered this a little bit, but we're going to go into more detail now. All right, so again, you have to upload your drawings, and they should be clear. All right, so VSEPR theory. VSEPR theory is valence shell electron pair repulsion theory. This is how we determine the shapes of our molecules. The shapes are determined by they minimize repulsions and maximize attractions. So it's the point. All the bonds are at a certain angle that will minimize repulsions and maximize attractions. So these are not just random shapes that are put together. We follow a chart, which is why I'm trying to set this up with the electron groups to help you understand how to read the chart. There are 2 types of geometries you're going to have to look into, because as you can see, if I go back up here, they're here and here. So we're going to take a look here. There is molecular geometry. Molecular means just what it is. It's the molecule itself. It does not include lone pairs. This is the shape of the molecule. And electron geometry means exactly what it sounds like. It's all the electrons. So the attachments around the central atom, and molecular applies to central atom as well, includes lone pairs. And so it can be different from molecular. If you have lone pairs on a molecule on the center atom, the molecular and electron geometry are not going to match. If you have nothing but bonds, no lone pairs on the center atom, the electron geometry and molecular will match. Okay, so I want to show you here how specifically this looks. You have normally we would draw it like this, right? But in reality, it's actually like this. The lone pairs, there's a lone pair here and a lone pair here. What you don't understand is that these lone pairs take up a lot of space, more than bonds. So the way that we draw them is with these little petals, but really they would be really big if you want the truth. Enough to push these bonds away from this area. But the thing is, you have to know which geometry you're looking at. So if you look at molecular geometry, it's called bent. So it's like this, but we don't draw the electron pairs. It's bent, but you don't see them. Electron arrangement is actually tetrahedral because we have 4 electron groups. So 4 electron groups will give the electron arrangement tetrahedral, and you'll understand when I show you the chart where these names are coming from. But if we only look at molecular geometry and we do not look at the lone pairs, then it's bent. So there's a big difference here on these. This is the chart that I use, and I'm going to show you how to use this. See the fancy word electron groups? This is what I was setting you up for. So we have electron groups, bonding groups. Now it doesn't matter if it's a single, triple, or what, it's always counted as one. Lone pairs, electron geometry, molecular geometry, approximate bond angles, and then some examples. So this is how you use this. You count your electron groups around the center atom. So let's say that we looked at one center, even if you had multiple center atoms, you're going to count each one separately like I did with a couple slides ago. Because what you see here is if we go back, this geometry is not going to match this geometry because this one only has 3 and this one has 4. So you can have different type of geometries in one compound. Okay, so we look at the electron groups and we count how many groups are around the center atom. Then you count how many bonding. Think of bonds. We are not specifically talking about single, triple, or double. We don't care. It's just a bond. And then you count lone pairs. And if you see there's 1 here, this is only for 2 electron groups around it. 3 has a couple things. 4 has a couple things. 5 has a couple things. And 6, and it goes down to 8. But right now we're not going to worry about that. So find the numbers, match electron group, find your numbers that match bonding, find your numbers that match lone pair, and then you can see what your geometries are for electron and molecular. So let's take a look at water since we already discussed it. Water has 4 electron groups. We have 1, 2, 3, 4. So I'm going to go down to 4. I have 3 options here. So I need to know how many lone pairs and how many bonding groups. I have 2 bonding groups and I have 2 lone pairs. That gives me a tetrahedral, a tetrahedral electron geometry, and it has a bent for molecular. This is exactly how you do it. So when you have to go and answer these parts, you know how to answer them. So this is where the Lewis structure comes in, and you have to be careful because if you guys decide to look some of these things up online, not everything shows lone pairs. So you need to make sure that what you find is actually correct. Because I realize some people may do that. But honestly, you're hurting yourself if you don't know how to draw these because it doesn't go away. Unless you're not planning to take any more chemistry and you can survive without doing Lewis structures. But if you can't, it never goes away. And for my students at the ones that are not in Chem 24, if you go into another the other college I teach at, if you go into 111, this will come back. Okay. So here are just some shapes. As you can see, there is carbon dioxide. It's got 180. It's considered linear. And then you've got bent, which is the same as water, has bent on here. But we don't look at lone pairs. So to tell you the truth, I don't know if this one has any lone pairs on it, but it must to have a bent. Because right now I can't think off the top of my head. But this is a bent, and this is a bent. And you got trigonal pyramidal. Trigonal pyramidal, it's not showing you that the lone pairs exist here. So this is what molecular geometry does not look at lone pairs. And electron geometry does. I know that these are really crappy pictures. I tried to get better ones and I just couldn't get them. But you can get an idea that electron counts the lone pairs that are on these molecules. And they kind of look like petals with 2 dots in them. Okay, so how do you read this if you have a molecule with more than one central atom? So I'm going to show you here with ethanol. Again, you count what's attached to it. So this would be a 4 bonding groups, 0 lone pair. This is tetrahedral and tetrahedral. If it doesn't have lone pairs, the geometries match. Now we're going to go to carbon here. It's the same as the first one because even though this is oxygen, we're not interested in what the atoms are around it. We're counting the interactions. So this is also tetrahedral on here. And because it has no lone pairs, it's also going to match, the geometries will match. Now we're looking at one that's a little different. We have 1, 2, 3, 4. So we still have 4, but this one has lone pairs in it and 2 bonds. So we're going to go to 4 and 2 and 2. So the electron geometry is tetrahedral like the others, but the molecular geometry is bent because what you actually see is this one's going to kind of bend out if you were to do the shape of it. So a molecule can have different geometries throughout the whole thing if it has more than one center atom. Okay, one more thing I need to cover. If you're given a complex compound, usually how it's written is how it's spelled out. Sometimes they don't and they make it hard and you have to figure this out. But so we have NH2OH. What this means is that there's an N. The N has 2 H's surrounding it and it's attached to an O. And that H is attached to the O. Here we have CH3CH2OH. Here we have CH3, CH2, O, and H. And sometimes they don't show the lone pair, sometimes they do. So how you're given the molecule is usually how you set it up. If you're not giving it to you like this, for instance, we can say this is NH3O, then you would have to figure out how many compounds you can come up with this. And you can come up with probably quite a few on some of these. So you'd have to wonder what the problem's really asking of you. But generally in chemistry, we tend to write them out the way that they are written out in Lewis structures. And that's kind of something that might be able to help you. Okay, so let's look at electronegativity. If you have a compound, the center atom is usually the least electronegative. The more electronegative atoms are always I don't want to say always, but most likely always at the end because they like to pull all the electron density and it makes it easier to do that. If you're ever confused, look up your electronegativity chart and see what has the lowest value and doesn't have more than one of it, and you can usually find out that which one is. So what I mean by more than one is that you don't want to pick, you can't pick H's. H's are never in the ball game. But let's say you have a C and an O. You're going to check the electronegativity here on those. If you had a compound, I'm trying to find one here, that had, oh, I can't find one. If you had chlorines around here, and you're trying to figure out which is the center atom, you would look at electronegativity. Chances are it's the boron because there's only one. And chlorine, which one do you pick to be the center atom? So when you've got more than one of the same atom, it's usually not the center atom. Okay, so here again, fluorine is the highest electronegative atom on the chart, and that means it will pull all the density away. So if you're doing a tug of war, it's going to be stronger than any other atom that's on the periodic table. So it's not going to allow a balance, and it's going to create a dipole, an uneven separation of charge in the bond by pulling it towards itself and leaving the other atom it's attached to with not as much electron density, creating a partial positive charge on it. Okay, so I want to show you. What is the central atom of POBr3? This is exactly what I'm talking about. If you get confused, look up an electronegativity chart. Here is the values, and you can see that phosphorus is the lowest in electronegativity. And because bromine has 3 of them, most likely it's not going to be that. And oxygen is the second most electronegative atom, so it's definitely not going to be that one. So phosphorus would be in the middle, and then you would work around that. Okay, so now we got to talk about bond polarity and dipoles. When 2 atoms are bonded together, there's no, it's not going to be a polar molecule, because if it's a tug of war, think of it as twins that are matched identically. I know twins are not always, but let's make believe that these twins are exact. The tug of war is never going to go anywhere because they have the exact same strength and endurance. So this is a nonpolar molecule when you look at B. But when you look at something like HF, hydrogen, fluorine has a value of 4.0, hydrogen has a 2.1. This creates a difference. And when you look at this, you can see that there's a big shift in electron density. Purple is where it's most positive. Red is where it's most negative. And you can see there's a big, huge red cloud because it's pretty much pulled the electrons so close to it that it leaves this portion partial positive and partial negative. And this is where we draw the delta sign with a plus sign and a negative to indicate which side is being partially positive and which side is partially negative. Yet there is still a bond. The bond is not broken. There's just an uneven tug of war between those for those electrons. All right, so if we look at molecules that have a center atom, and that's mostly what we're looking at here. Excuse me. I'm still getting over my cold. We have carbon, and carbon is a center atom. It was lower in electronegativity than oxygen, and this is CO2, carbon dioxide. Oxygen and oxygen have equal values, so they are equally pulling on this compound, on the carbon, the electron density away. So you can see where carbon is partially positive, the purple, and the oxygens have red and red, but they're equally pulling on this. And I'll come back to that in a minute. Now we have water. Water, the hydrogens the electrons are being pulled away from it, so it's purple down here, and towards the oxygen, which is really red. So this causes water to be very polar because there's an imbalance on this molecule. However, this one, even though it has polar bonds on it, it is not a polar molecule. This is nonpolar because this is being pulled this way, this is being pulled this way in the equal strength, so they cancel each other out in opposite directions. So this one is actually nonpolar, and this one's polar because there is no canceling out. Everything's being pulled in one direction. Okay, so to determine if a molecule is polar or nonpolar, it is useful to look at the structure itself. Nonpolar compounds tend to be symmetrical, where they're being pulled in. So if you see, they have atoms that all match. There's no balance or shift of balance on them, and they tend to pull in all directions. That will cause the compound to cancel out it being pulled with the electron density being pulled away from it. So it can start out with a polar bond, but in the end, the molecule itself can end up being nonpolar because it's been canceled out. That's very important to understand. So here is carbon tetrachloride, and carbon and chloride. There is a polar bond going on here. The chlorides are pulling the electron density in all directions, but they're all pulling equally, and all of them are canceling out. Even though you can't really see, they're all being pulled in equal directions or opposite directions of it, and it cancels it out. Same as BF3, boron trifluoride. And molecules that are identical to itself, that are bonded together, they're nonpolar because the tug of war is never going to win on it. You need one of these to be a different atom, and that's usually where it starts with the non-symmetric, and now the balance is going to shift. So here's a nice way to visualize what I'm talking about. If you have a tug of war and the strength is equal, it's nonpolar. Nothing's ever going to happen. If you have, because the electron density is going to sit exactly in the middle. If you have a team that wins, so this guy's bigger, he's going to pull, the electron density is going to go towards him. He's going to win the tug of war. If you have a rope with 3 and they're all pulling equally, nothing's going to win. No one's going to be able to move the electron density. It's going to be nonpolar. If you have one that has 2 people, it's going to pull every electron density this way. It's going to make it polar because there's not balance to cancel it out. And then you have 2 teams that win, so you have 2 strong atoms and one that's not. Then that's going to pull in 2 different directions and leave the other one partial positive, and it's going to be a polar molecule. If you get confused about bonds, here's electronegativity chart. You subtract one from the other, always have a positive value, so it doesn't matter which way you subtract it, just make sure that it's an absolute value, make it positive, and you can see the difference. And then what you can do is you have a chart. You can see this is 1.9, this is 0.9, 0.7, and 0.4. There is a way to know what these numbers mean. This is it. If it's nonpolar, it's going to be less than 0.5. If it's between 0.5 to 1.7, it's considered polar, partially polar, slightly polar. There's different ranges in polar, but it's polar. And if it's ionic, it's going to be above 1.7. So if you see here the bond symbols, this is equal. The electron dots stay in the middle. Here is polar with the polar bear, and B is going to pull it because it's got more strength in the tug of war than A does. And ionic, the electrons completely come off, and it's going to go to B. So this is something that can help you when you look at these here. I will tell you that if you go online in different books, these numbers change. Some will consider nonpolar at 0.4 and below. Some consider 0.5. I don't know why all of these change. This might be 1.8. I've seen it as considered as 1.9. It's just weird. And then here's just some pictures of polar with the partial positive and partial negative. So you can see that this actually has electron lone pair on it. So it's pulling everything this way. These have 2 lone pairs. It's pulling. These have a lot of lone pairs around it. And then you have non-polar, which as you see is very symmetrical and it will cancel out. Here's your electronegativity chart if you wanted to take a look at that. Remember, it increases this way and decreases down. You can see fourth, the noble gases are never considered in this, at least not at this level of chemistry. And your highest is 4.0 is this fluorine. Oxygen is next. Okay, now the dipole moment. So if we were looking at polar covalent bonds, that's a shift in the electron density. The electron density is pulling it away from one and towards another. That's creating a separation of charge. So for water, you see these arrows, these also indicate, unlike the little signs, the partial positive and partial negative, you can also use these arrows. The arrows point towards the more electronegative atom and away from the least electronegative atom. So you see hydrogen is not as electronegative, chlorine is, so it's going to pull that way, or you use these little signs. But what this means is that this one cancels out, so this cancels and this cancels, this is nonpolar. But what if they don't? Then they usually will sometimes show a big arrow showing that all the electron density is being pulled towards one atom and away from the other. So that's all. But these indicate dipole moments. This is a dipole moment. This is not. There's a dipole moment here because it's all being pulled this way, and there's nothing else to cancel this out because there's only 2 atoms. This one gets canceled out because there's matching atoms, and the tug of war never goes anywhere. This one is not because oxygen, if you want to think of strength, is stronger than the hydrogens. So it's pulling it. There's going to be a bond dipole on this one and a bond dipole on this one. So there is an overall dipole moment on this compound. Found this online. I couldn't break it up because this is really scrunched together. But the purples indicate that there's a dipole moment, and the black arrows indicate that things cancel out on it. Okay? And here are some things they're generalizations, so they don't always apply, but some things that might help you. If there's a carbon in the molecule, it tends to be the central atom. Oxygen, sulfur, phosphorus, carbon, and nitrogen can have double bonds. Oxygen, carbon, nitrogen can have triple bonds. Carbon should never have a lone pair on it. We're not in that chemistry. If oxygen has a single bond, it tends to have 6 electrons around it. If oxygen has a double bond, it tends to have 4 electrons around it. I call them ears. Hydrogen never has more than 1 bond, ever. It's a terminal atom, meaning it's at the end. It's a bookend. And bonds on a molecule can be polar, but the molecule itself can still be nonpolar. The bonds will cancel out. I hope this helps understanding this lab. This is why I broke it up, because this lecture is a lot longer than what the lab is. Okay? Thank you.